Hello, everyone. I'm Wenjun Li. I'm from Chemical and Biological Engineering Department at Iowa State University. I thank for this chance to give a presentation on the ACS 2021 fall meeting in the Division of Catalysis Science and Technology. My presentation's title is Electrocatalytic Hydrogenation of Furfural Compounds from Mechanism Study to Paired Electrolyzer Design. So my presentation has two parts. The first part is on the electrochemical reduction of furfural on the metal electrodes, focused on the copper electrode. As we all know, hello everyone, I'm Professor Wenjun Li. I'm from Chemical Engineering Department at Iowa State University. I'm very happy to be here to give a presentation in the ACS fall meeting this year in the Division of Catalysis Science and Technology. So my presentation title is Electrocatalytic Hydrogenation of Furfural Compounds from Mechanism Study to Paired Electrolyzer Design. First, I'd like to thank my former students, David and Xiaotong Chatterton, and my current students, Heng Zhou and Ding Han, and Professor Eric Cochran. So my presentation has two parts. The first part is electrochemical reduction of furfural on the metal electrodes. As we all know, hello everyone, I'm Wenjun Li from Chemical Engineering Department at Iowa State University. I'm very happy to be here to give my presentation on electrocatalytic hydrogenation of furanic compounds from mechanism study to paired electrolyzer design. I'm honored to give my presentation in the ACS fall meeting this year in the Division of Catalysis Science and Technology. First, I'd like to thank my former and current graduate students, David Xiaotong Chatterton, Hengzhou Liu, Dinghan Li, and my colleague, Eric Cochran. So my presentation contains two parts. The first part is focused on the mechanism study of electrochemical reduction of furfural. As we all know, furfural is listed as top 10 most promising bio-based platinum molecule. It can be obtained from carbon-5 sugars, from lignocellulose biomass. From furfural, we can get furfural alcohol, which can serve as a precursor for ricin synthesis, or 2-methylfuran, that is promising biofuel additive. So first, let us compare the catalytic hydrogenation of carbonyl group using thermocatalytic hydrogenation and our electrocatalytic hydrogenation, ECH. So first, we need to increase temperature to dissociate hydrogen absorption, because molecular hydrogen first need to be chemically absorbed on the catalyst surface, and then the absorbed hydrogen attacks this carbonyl group to get the reaction, hydrogenation product. As a comparison, the hydrogen source does not need to come from molecular hydrogen. It just comes from the acid electrolyte. We get absorbed hydrogen, and this hydrogen can hydrogenate the carbonyl group and get the hydrogenation product. So the advantage for ECH is there's no need to use molecular hydrogen. It can operate at relatively mild conditions. Now let us compare ECH with hydrogen evolution, HER. As we know, for the ECH process, we need chemical absorbed hydrogen to hydrogenate this carbon-oxygen carbonyl group. We need 2 dissolved hydrogen to get alcohol product, or furfural alcohol, or 4 absorbed hydrogen to get methylfuran. But during this hydrogen chemical absorbed process, hydrogen gas can evolve from the catalyst surface, through the Balmer step, Pravorsky step, and Tafel step. So there might exist a direct electron reduction process through a proton-electron coupled process. Starting from furfural, we can also get furfural alcohol, but in the same time, we can get one dimer, as shown here. So we use Faraday efficiency FE to represent how much electron transferred to the desired product over the total electron transferred. Let's say there is still understanding gap between organic electrochemistry, through electroreduction process and the electrocatalysis, especially for the alcohol's production. So my next slide, I'm going to show you how we try to, elucidate these basic reaction mechanisms. So we basically conduct our research in a H-type cell using a proton exchange membrane to separate the anode and cathode. We definitely focus on the cathode. We use high purity copper foil as the electrode. We can use either sulfuric acid or buffer sulfite with some isonitrile aqueous solution. Then we can, use a cold trap to trap the products. We use HPLC and NMR for liquid product analysis and online GC to on-site quantify the produced hydrogen from water reduction. So the temperature is room temperature. So basically, first we varied the applied cathode potential at low pH at 0.5. As you can see that after we add 0.05 more furfural, we get actually early onset potential, which indicates some ECH or ER products can be produced. As you can see here, the Faraday efficiency to furfural reduction decreased as more negative potential, and the selectivity to methylfuran actually increased, compared to the other furfural products, furfural alcohol and hydrofuran, that's a dimer, with more negative potential, the selectivity to Fe increased. Dimerization was a minor contribution at these conditions, but we also find that the hydrogen production at is more is stronger at more negative potential. Then we kind of change the initial furfural concentration and the electrolyte pH. We tune the protons concentration. We find that the Faraday efficiency to the HER decreased at a higher furfural concentration, as you can see here, and selectivity to furfural alcohol and the dimer hydrofuran increased with a higher furfural concentration, and at the high pH and furfural concentration favored furfural alcohol and hydrofuran's formation, as you can see here. So there must be some fundamental mechanism behind it to distinguish the furfural electrochemical reduction pathway. Especially the origin of the products of furfural alcohol. We need to distinguish the ECH process and direct ER process. So we consider that the electron transfers through inner sphere, that's pretty much just for ECH or HER, that need a direct contact between your reactant molecular with your electrode. In our case, it's copper. But through the outer sphere process, there is no direct interactions between reactant molecular with the electrode. So that's more easy to happen on the ER process. So we introduced a technology called self-assembled monolayer, because that a monolayer, SAMS, can block the reactant directly access to the electrode surface, but may allow the electron tunnel. So we basically found some literature, especially from the elegant work from Alan Bard group. They use some cell-based SAM to modify their gold electrode. So they compare the inner sphere hydrazine oxidation. You found that even short chain carbon-3 cells can quite surprise the hydrazine oxidation on the gold electrode, while for the outer sphere ferro-acetomethanol oxidation. So even you use a longer carbon chain cells, it kind of surprised this outer layer outer sphere's electron transfer, but it's not that severe compared to inner sphere-based hydrazine oxidation. So this can give us some idea that we can use this modified self-assembled monolayer to distinguish the reactions mechanism. So basically, we use a cell monolayer to block the access of the copper electrode surface, and therefore we can inhibit the inner sphere ECH reactions and generate only outer sphere, that is direct ER product. So we basically use a different type of cells, including MDA, the long carbon chain one, MBT, and MPA. So as you can see here, the current suppressions is following the directions. MPA is lower than MBT and MDA. With MDA, even without addition of furfural, it can be completely block all the active sites. I mean, even HER is suppressed. Well, if we added furfural, we observed a similar trend that indicate that for some outer spheres based direct electron reduction can be suppressed, especially with longer carbon chain cell monolayer modified electrode. Okay, then we found that both MPA and MBT can successfully suppress Fa and MF production quite significantly, but while the hydrofuran, that's the dimer rate, was unchanged. You can see, there are orders of magnitude change for the MF and FA's production, while the dimer's production rate was not changed. So also the FA and MF formation, requires direct interaction with the copper surface. That's a strong hint, we obtained from this cell modified copper electrode experiment. While the hydrofuran, that's dimer's production, likely occurs through the outer sphere process. We also change the pH. Basically, we get the same result. So another technique to clarify the role of adsorbed hydrogen is to use hydrogen's isotope, that is deuterium. So we basically use hydrogen and deuterium isotopic study to study this mechanism. As we know, deuterium evolution reaction is sluggish, more sluggish as compared to hydrogen evolution reaction. There is about 87 millivolt, voltage difference. So basically, we applied deuterium, we obtained a similar trend that indicate that electrocatalytic hydrogenation or deuteration, you definitely need some chemical adsorbed hydrogen or deuterium to participate into the reaction. That's is hallmark for ECH reaction. So again, we try to clarify that, for methylfuran and furfural alcohols products that goes through the ECH process. Well, for the dimers, that's from electroreduction process. So we also examine the furfural reduction products on the HER inert lead. The rationale is, on the lead electrode at very lower potential where HER does not occur, but you probably still have some, outer sphere based, product direct electron reduction, because in that process does not involve chemical adsorbed hydrogen on surface. That is okay in this potential, negative 0.55 volt, because at this potential on lead, HER does not occur. Let's see what are the products. It's very interesting to find on the lead electrode, we actually just observed the dimer and some other, trimers or resins instead of methylfuran and Fa. So because lead has a very weak hydrogen absorption at this potential, and therefore the adsorbed hydrogen is not present to participate in furfural reduction. So this kind of help us to provide some indirect evidence to exclude MF and FA is go through, outer sphere electron transfer process. They must be produced through ECH process. While on the lead, only the dimer and other, trimers, and resins, and very small amount of Fa, smaller than 1%, basically no MF observed. This gave us the, another evidence to show that MF and Fa are produced through ECH, while the dimers and other, resins produced from ER process. Finally, we distinguish the ECH reaction pathways to the MF because from heterogeneous catalysis, furfural alcohol is believed to be a reaction intermediate to methylfuran. But what can happen on the chemical reduction of furfural on copper electrode? So we basically found that with reaction duration increased, the selectivity for the all the for the methylfuran, furfural alcohol, and the dimers, keep constant with even very high at very high furfural conversion. This indicates that the furfural alcohol and the methylfuran are produced from two independent processes. It's more likely a parallel reaction instead of a series reaction. So we tried just directly put furfural alcohol in the system. We apply the potential. Let's see what the product to see if methylfuran is a product. It's consistent to or agreed with our expectations. There's no methylfuran was produced from furfural alcohol, while the hydrogen is dominant product. So that means furfural alcohol in this system is not the intermediate to the methylfuran. So finally, let me summarize the first part of study. So hopefully I have convinced you that both electrocatalytic hydrogenation ECH and direct electron reduction ER of furfural are operable on the copper electrodes over a wide range of conditions. MF and FA are produced from ECH process, while the dimer from directly electron reduction ER process. So both methylfuran and furfural alcohol are likely formed from parallel pathways. So next, I'm going to briefly present our efforts on paired HMF reduction and oxidation to get two usable monomers for bioplastic synthesis. So the goal is to achieve efficient conversion of HMF, that is a furfural-based compound, to two monomers at the two electrodes in a paired flow electrolyzer. So we have developed supporting nanoparticle electrode for electrocatalyst for HMF cathode reduction. We reduce HMF to BHMF, and we also paired HMF hydrogenation and HMF oxidation to get FDCA. As FDCA has considered a promising monomer to synthesis bioplastic. Okay. So we actually look at the FDCA HMF's oxidation to get FDCA with water oxidation to get oxygen. That's oxygen evolution reaction. We have a huge thermodynamic potential gain, because OER occurs at an overpotential around 1.2 volt, while HMF to FDC is actually, is a more negative potential. So we have this thermodynamic potential gain. Also, I want to highlight, the electrons utilization efficiency. We called EE. So EE is the electron transfer to the desired product to the total electron transfer. So that means if we can, suppress hydrogen evolution and oxygen evolution from the water, we use the same feedstock HMF to get FDC as anode and BHMF as the cathode. So basically, we can use the electron twice. So theoretical, EE or the paired electrolyzer for this particular case can reach up to 200%. But however, we found a challenge for the paired electrolyzer if we use some, solid noble metal catalyst, for example, palladium catalyst. So we have published the paper in green chemistry years ago. So we found that, the operating potential for the two half of the reaction in one electrolyzer cannot be independently controlled through the external circuit. So in other words, that, so if the two electrode reaction, okay, like HMF reduction to get the BHMF, the desired product is potential dependent on your cathode potential. Well, on the palladium-based catalyst, if the HMF oxidation is also potential dependent, as shown very clearly here. Okay, at the low potential, we basically just get FFCA, not desirable FDCA. Only at a given higher potential, we get high conversion, high selectivity to FDCA. So that means we have to find a smart way to make one electrode reaction, is potential independent. So our approach is we use redox mediator like TEMPO to facilitate this indirect oxidation. So just show you this TEMPO mediated reaction. So as long as TEMPO is oxidized to get TEMPO plus can further oxidize HMF to oxidation products. As long as this process proceed at long time, enough electrons can be depleted, we can gradually oxidize HMF to get FDCA. To elucidate this concept, we change the anode potential by using this TEMPO mediated process. We found that at different potential, for example, from 0.7 to 0.9 volt, basically we get very similar selectivity to different products. I should say that this process is not proceeded at long time. So the FFCA, the reaction intermediate is the final product. As long as we proceed, we supplied enough charge, the coulomb is enough, we can convert all the HMF or oxidize all the HMF to FDC as shown here. So basically we replace the noble metal solid catalyst by using some homogeneous TEMPO mediated process to pair the two electrodes reactions. So we further use H-type cell to show that HMF can be reduced on the silver electrode to get BHMF. Well, the potential needed is less negative than HER on silver. Well, we use this mediated process, TEMPO mediated HMF oxidation. We just use carbon electrode. That oxidation potential is lower than the OER on the carbon electrode. That provides us with some base to pair them together. Because taking advantage of the kinetics, a paired HMF electrolysis cell can be operated with as little as 1.6 volt. You just see the potential difference. Well, no apparent gas, hydrogen gas and oxygen gas evolved from the two reactions. So finally, I'm going to show you, we can compare the paired electrolyzer with unpaired electrolyzer. We get over 187% of electron efficiencies for this paired electrolyzer. Let me summarize this part of research. First, we applied supported silver nanoparticle for HMF hydrogenation to get BHMF. Then we demonstrated a paired batch and flow HMF electrolyzers, and we have found high electron efficiency up to 187% for generation of bio-based monomers from HMF, BHMF, and FDCA. This is a promise for distributed chemical manufacturing. So we, my new graduate students, Heng Zhou and Ding Han, work together. They kind of extended silver nanoparticle catalyst to power silver electrode and, integrate HMF reduction with some other oxidations, and integrate paired electrolyzer with hydrogen production to integrate some heterogeneous catalytic reduction reaction by using molecular hydrogen. So we published our recent research in green chemistry, electrochem, and we are invited to contribute to a review article in current opinion in electrochemistries. So our overall view for this project is we can start from very fundamental research to do ECH of biorenewable feedstocks like furfural or like meconic acid from my colleague GP Tanzania's group. We applied different electrochemical techniques, we studied the mechanisms, and then we developed some real-world catalysts like silver nanoparticles or power silver. Then we build up some paired electrolysis to save the energy cost and improve production efficiency, including to improve the electron use efficiency and production rate to finally achieve sustainable distributed chemical manufacturing by using mass-based feedstocks. Finally, I'd like to thank my former and current students, Xiaotong, David Chatterton, Yang Qiu, Dinghan Li, and Hengzhou Liu, and my collaborators, Dr. Tanzania, Dr. Cochrane, Dr. Shanks, and Matthew Panzani. My funding source comes from NSF. I also get generous funds from Ames Lab and some internal funding from our state. Thank you for your attention again. I will be happy to answer your questions.